All right, it is 8:42, so let's get started. Um, Hello, this is great. Uh, Sorry for missing all of last week. Um, Hopefully you all enjoyed not having to wake up at 8:30 in the morning, or I guess whatever other time it might be in whatever time zone you might be in. Um, uh, but we're back now, so hooray for that. Uh, Also, hopefully you all got a chance to look over the posted lecture about sorting algorithms. Um, I didn't see any questions about that in Piazza, but I guess if there are questions about any of the stuff on that lecture, um, now's a great time to ask it, or you can also post it on Piazza or um, maybe office hours or something like that. Um, cool. What else? What else? What else? What else? Oh, yes, I do have office hours today after class from 10 to 12. So if you want to stick around for that, stick around for that. Um, the exam is coming up. It's 1 week from tomorrow during class time. Um, there's a number of people who are, if you've talked to me about taking it at a different time, uh, then you will take it at a different time. If you do need to take it at a different time, please uh, talk to me by like the end of the day tomorrow. So 1 week before the exam, um, so that we can get all of that sorted out. Um, yeah, I will go over probably in the lecture tomorrow or Friday. We'll talk about what you should expect from the exam, um, how long it'll be, what content it'll cover, and so on. But for the most part, you can expect it to cover stuff like through this week. Um, yeah, so we'll talk more about that later. I'll release a couple of practice exams from past semesters, but it's probably important to know that the order they might have covered things in last semester might be different, and the format of the exam will almost certainly be different. So it's sort of good to like practice. It's maybe useful to practice the material and practice the content, but maybe not so much as a template for what you expect this exam to look like. Um, Cool. Other course logistics things. The problem set was due, I guess, last Friday. I think almost everyone turned that in. The first programming assignment was due yesterday at midnight. Um, just a reminder, you do have until July 6th, which is Saturday, to turn it um, in exchange for using up some of your late days. Um, so yeah, if you haven't already done that, I would encourage you to get that in. Um, the second programming assignment I posted like maybe half an hour ago. That'll be due on the 15th. So I would encourage you to also take a look at that. Uh, we're going to be talking about the content for it probably today or in the next couple of days. Um, but you should be able to get started with it. Um, yeah. Uh, Write-up. Yes, of course. Write-ups. People can submit write-ups. There was apparently a flood of write-up submissions yesterday because the last time I checked, there was like five, and now there's like 30, which is great. I'm very happy everyone's doing the write-ups. Feel free to continue submitting them. Like, I'm not like, there's no late penalty for yeah, it's extra credit. So just kind of submit it if you have it, I guess, is the main thing. Um, there will be a write-up for PA2 as well. Um, yeah, okay. So that's project stuff. Um, what else do we have? Oh yeah, attendance polls. There's going to be an attendance poll today. I just made a thing for it. I know there hasn't been one for like a couple of weeks at this point. Um, I have finished going through all of the attendance polls through the 18th, so it's just the last two from the 20th and the 21st um, um, that I haven't fully gone through yet. So if you submitted one after I published the grades for that, you probably will not see it. Like in the grade book or whatever. So yeah, I mean the purpose of the attendance polls is to kind of like keep everyone on track. So I'm not super concerned about like being a little bit late on those either. But if you do happen to submit one and you haven't seen a grade for it, or if you've resubmitted or something like that, and you haven't seen your grade updated, you can send me an email and I'll take a look. Um, Homework grades, I think my TAs are pretty much finished grading the first homework or the first problem set. The late deadline for that is tomorrow at midnight, so Wednesday, July 3rd. Um, After the late deadline, we will release the grades for that. And we'll release like an answer key and everything as well, so that you can sort of take a look at if you like, you can sort of see what you missed and why you missed it and whatever. I'll leave regrade requests open on that for a week, so you'll have until the day of the exam if you want to file a regrade. Um, and yeah, I would encourage you to not spam regrade requests. Only submit one if there's like if the answer key says that you should have gotten points for something and you didn't get points for that. Like, don't. Yeah, I mean, yeah. Anyway, um, don't abuse the system, I guess, is what I'm going to say. Um, okay, I think that's all I have for course logistics. Are there any questions or concerns or clarifications about anything along those lines that I can help clear up before we move on to content? Cool. All right. If not, I guess, oh, also, are there any questions or concerns about any of the sorting algorithm stuff or any of the like lecture? I guess it was just the one lecture, but the lecture from last week or like the lecture slides that I posted. All right, sweet. And of course, for those of you watching the recording, you can't ask me questions live, but feel free to post on Piazza or send me an email or whatever. And if it's content related stuff, like you can also go to TA office hours or my office hours. Either is fine. Um, okay, so I figure we can get into it now. I'm going to create a whiteboard and we're gonna go back to talking about trees. Okay, can everyone see the whiteboard? Perfect. All right. Okay. So, from the lecture on last Friday, which at this point was 11 days ago, 10 days, 11 days, something like that, a long time ago. We talked about, we sort of introduced trees, binary trees and k-ary trees. And then we had some definitions, right? So we had this idea. So I guess like a binary tree is something where every node has at most two children. Um, we call the uh, like like this is a child. This node is a child of this node. Um, this node is a parent of this node. The root is a node is a node without any parent, and all nodes without children are leaf nodes, right? So we've got root, we've got leaf, we've got child and parent relationships, and then we've got like ancestor is just like a parent of a parent of a parent. So like the root is an ancestor to every other node in the tree. Um, right? We talked about, I think, directed and undirected trees. Directed just means that these arrows, like these connections have direction to them. Um, uh, for our module on trees, we're mostly just going to be considering directed trees, but when we talk about graphs, we'll kind of generalize this to undirected trees as well. Um, and we'll sort of see how you can like get from one to the other. Um, yeah, okay. So I guess some more definitions that we had. Right, okay, so I guess we had like binary trees. Um, and within here we had complete, almost complete, perfect, right? So complete means actually, does anyone remember what complete means? Balanced? Okay, balanced is part of it, yeah. Actually, I guess you could just say balanced because if it weren't, yeah, that's fair. Um, balanced, all leaves at the same depth. Yep, everything has two or zero children, a total of 2 to the n minus 1 nodes, right? Um, almost complete. Do we remember what almost complete means? So I guess maybe I'll draw like a complete binary tree is something that looks like this, right? Or if I add another layer, I have to add everything in that layer, right? So the depth is 2, maybe we'll call it 3. And then it's got 1, 2, 3, 4, 5, 6, 7 nodes. So 2 to the 3 minus 1, right? And of course it's balanced. Um, so if this is a complete tree or a complete binary tree, almost complete means that I've got everything except I'm allowed to not have some of the nodes at the very end, right? So some of the rightmost children are allowed to be missing. So for example, this is almost complete, right? Um, but if I were to add another node like here or something, this would no longer be almost complete because um, I would need to fill this. I would need to like put something here before I can put something down here, right? Um, so that's almost complete. Right, so we can say maybe complete except for some rightmost leaves. And then um, perfect binary tree. Do you remember the definition for that? Um, yeah, okay. So a perfect binary tree is one where every node has 0 or 2 children, right? So it's like properly binary. Um, so for example, every complete tree in particular is perfect, but an almost complete tree might not be perfect, right? Because we might have something like uh, this. This is almost complete and perfect. This is almost complete but not perfect. This is almost complete and perfect, right? So complete is sort of the strongest version of all of those. We talked about how you can sort of densely pack trees into an array if you have a bound on the size of the tree. This in particular assumes that your tree is going to be almost complete, but if you have a tree that's not almost complete, you can pretend that it is by like by padding it out, right? So if I have a tree like this, something like this, right? This is not almost complete because I can't add this node until I've put it, like I can't put a node here until I've put one here. By the way, everyone can see like where my pen moves, right? Like if I just use it to like point at something or like gesture at something. Um, oh, you can't. Shoot. Okay. Well, okay, rip. Okay. Um, okay, I'll yes, too many curses. Of course. That yep. Okay. That's very good to know. Okay. Let's there's like a laser pointer tool or something. Wait, maybe there is. No, there isn't. Yeah, okay. So we can't insert there's a cursor option above the pen. Am I just I can I just not see it? Wait, can you see it now? Can you see the pointer? Okay. Oh, well, oh, okay. Yeah, that's fine. I'll spend some time experimenting with this. Sorry about that. Um, yeah, so this is not almost complete because oh, if I click Z. Oh, yo, that's so cool. That is so cool. Okay, here we go. This is good. This is a game changer. Um, excellent. Okay, so yeah, this oh my God, and there's mode. Okay, this is really cool. Okay, I need to figure this out. Maybe after class. Uh, Zoom is Loki kind of goaded. Okay, so this is not an almost complete tree, right? Because we're not allowed to add this node here before we put something here. Um, but if we wanted to pretend that this was almost complete, like the thing stopping this node from existing is the fact that we need two children here, right? So we can just go ahead and add um, like two fake children, right? And these can just be some like sentinel values, or they can just like depending on what payload each node carries, right? This might be like a zero or a null or something like that, but like these pointers are not null. They point to actual like sentinel nodes, um, or like dummy nodes or something like that, right? And so now that I've put these in here, I can pretend that my tree is in fact almost complete, or like the resulting tree that I get is almost complete. Um, so uh, right, you can always pad out a tree to be a complete tree or to be an almost complete tree, or even, I guess, to be a perfect tree, right? Like if you've got a node with just one child, you just add a dummy child so that every node has either zero or two children. Um, so if you have some good concept of um, like a sentinel value or like a dummy node or something like that, you can just insert these to make your tree look the way you want it to. Um, yeah, okay. So if you have an almost complete tree, remember you can pack this into an array by, let's say we have an array. This is going to have 2 to the n minus 1 spaces. Uh, I mean, I can't count. This is 8 spaces, which is not 2 to the n minus 1 for any integer of n, but I don't care. No, you know what? I do care. I do care. I'm gonna delete this. There we go. Um, okay, so we put. Okay, that just looks gross. Sorry. You know what? I'm just not going to try to count. Okay, so we have an array. We can put the root in position 0 of the array, right? And then if you've got a node at position I, its left child, you just put in position, what is this? 2i plus 1. And its right child, you put in position 2i plus 2, right? So the root goes in 0, which means its left child goes in 1, and its right child goes in 2. Maybe let's do an example, right? So if you've got this almost complete tree, um, right? So A goes in position 0, its left child is B, so B goes in 1. Its right child is C, so C goes in 2. B's left child is D, so D goes in 2 times 1 plus 1, which is 3. And then E is the right child of 1, so that's going to be 2 times 1 plus 2, which is 4, right? So E goes in 4. And then we don't have anything here. So you can sort of pack a binary tree into an array like this. And this is nice because I don't have to follow pointers, right? I can just do an index calculation, right? So if I know what some node is, like a particular node is at index 3, I can do 2 times 3 plus 1, which gives me 7. I can say, oh, 7's outside the bounds of this array, so it doesn't have a left child, right? Um, and the reason I need this to be almost complete is because if, for example, it had a right child but not a left child, it would not be almost complete, but then I would have like something at position 8 but not at position 7, which doesn't make sense, right? Alternatively, if you want to pack a not almost complete tree into an array, then you've got to have some kind of like blank value in between. And so then instead of checking for whether it's outside the bounds of the array, you look up that index and then you check to see if it's blank or not. Um, so yeah, okay. In particular, if you watched the lecture on heap sort, we used this sort of dense packing, right? So you can take an array and you can think of it as a tree just by thinking of it as being an almost complete tree that's been packed into the array this way, right? So if I have like an array containing uh, maybe 3, 1, 4, 5, 2, or something like that, right? Um, I can think of this as the binary tree that looks like 3, 1, 4, 5, 2, right? I just go left to right, top to bottom, and I fill nodes in as they show up, right? And so this always gives me something that's almost complete. Um, and then of course for heap sort, right, we just do like operations on this tree, but these turn out to just be operations on the array. And so you can do everything like very nicely. Everything stays in the cache. Like you're not doing a bunch of like indirect pointer lookups and so on. And then you can free one block of memory. So there's nice aspects to this. But yeah, you can pack things into a dense array. So far, I think all of this is review. Sorry, I know I spent 20 minutes going over stuff that we already did in class, but I figured since it's been close to 2 weeks, it would be nice to maybe do a quick refresher. Are there any questions or clarifications about any of this stuff before we maybe start to move on to new content? Curious why the clarification is so important. That affect design choice. Wait, sorry, what do you mean? Does what affect the design choice? Oh, complete, perfect, and almost complete. Yeah. These are they're definitions, right? So sometimes you'll need to know for a particular algorithm that your tree is complete. And so it's important to like have the vocabulary to describe that. Um, or like, yeah, I mean they're just definitions. So for example, a heap requires you like a heap means that the tree you're going to be working with is always going to be almost complete. Um, if you know your binary tree is perfect, then you know that like that it's never going to have a node with just one child, right? So it's just kind of um, they're important in the same way that any kind of vocab is important. Um, which is to say, maybe not all that important, but probably worth knowing anyway. Um, any other questions before we move on? Okay. All right, so I figure we can talk about traversals now. Um, so I want to talk about tree traversals, and then if there's time, I want to start talking about search trees, like binary search trees. Um, and then we'll talk about, after that, we'll talk about spatial indexing trees. We're obviously not going to get to all of that today, but that's just sort of, I'm saying my plan for the week out loud. Oh, sorry, I completely forgot to mention this at the beginning of class. Thursday is the 4th of July. Don't come to class on the 4th of July. There's not going to be a lecture. Which I realize I've now canceled multiple classes. So I this time I will in fact record a lecture, and then you can watch that whenever you want. I meant to record one for yesterday, but again, I got home so freaking late that I couldn't. So the exam back. I'm not going to push the exam back just because that's going to mess with everything else that I have planned. But yes, what is a kilometer? I only think in freedom units. Uh, Excellent, 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 excellent. Okay, great. So, yeah, okay, let's talk about tree traversals. Um, I'm gonna move down here. Uh, okay. So in general, we can classify traversals into um, two categories, and then there's ones that don't fit into either of these, right? So these like classify based on like the order in which we traverse. Actually, maybe I should talk about what that means first. A tree traversal is something that visits every node of a tree, right? So um, it's just any like algorithm that we'll say maybe systematically visits, like processes or whatever, every node of a tree. Okay, so we can classify these by their order. So we've got breadth first, we've got depth first, and then under depth first, we've got pre, post, in order. Um, and then there's like other things that you can put here as well, because for any given tree, there's like, n factorial different orders that you can visit the nodes in. Um, and depending on your context or depending on your application, something might make more sense than another. Um, uh, but these are going to be the main ones that we care about, right? And it's also important to know that this idea of like depth first and breadth first, uh, these will apply to graphs as well, which we'll talk about graphs in a couple of weeks. But the same idea is going to generalize to even when your graph isn't a tree. Okay, so the idea of breadth first is you sort of go from top to bottom, and you visit things in order of how close they are to the root, right? So in order of how close the node is to the root, right? So um, I guess there's a bit of vocab that I didn't go over from last time. I think we went over it last time, but I didn't go over it today. How close the node is to the root. Does anyone remember what the word for that is? Depth, exactly. Yeah, right. So breadth first traversal visits nodes in order of depth, right? So what does that mean? That means if I have a tree like A, B, C, D, E, I'm going to visit these nodes I go A, and then I visit B and C, and then I visit D and E, right? Because A is at depth, I don't know, we'll call it 1, B and C are at depth 2, D and E are at depth 3, right? So I visit them in this order. Um, a depth first search, by contrast, um, uh, does not do that, right? So you can think of it as somehow um, uh, maybe visiting from like left to right, right? Or visiting leaves as soon as possible, or other things. But I think the best way to think about a depth first search is as one of these three, right? So pre-order, post-order, in order. So pre-order means you visit a you visit the parent before its children, right? So pre-order, parent, then children. So pre-order traversal of this tree would be we do A, and then we visit its children. So we look at B. Now we visited B, so we have to visit its children. So we do D and E, and then we go back up. We visit the next child of A, which is C, right? Post order is children then parent. So here we've started at A, so we want to visit its children first. So we look at B, but we want to visit its children first. So we look at D and then E, and then we can visit B. And now we have to visit A's other child, which is C, and then we can visit A, right? So these are sort of maybe counterintuitive to like look at when you look at the tree, but they make more sense in code. So we'll maybe go over some pseudocode for this. And then finally, is there a way to like, okay, whatever. I'm gonna put in order here because I don't want to scroll the tree off the screen. I guess I could zoom out, but I'm not zooming out. So in order is child, then parent, then child, right? So an in-order traversal of this is we visit B first, but to visit B, we have to visit D first. So we do D, then we do the parent, which is B, then we do E. And now we visited the left side, so we visit A, and we move on to the right side. And so that's just C, right? This is an in-order traversal. Each of these have like semantics, like they represent or there's like good ways to think about when you would care about each of these traversals. So maybe we can talk about that, or maybe it'll make more sense in pseudocode. So yeah, okay. Let's look at pseudocode first for the depth first traversals, right? So maybe I want to start with depth first pre-order, right? For some tree T. So if you remember, I visit the parent and then I visit the children, right? So I'm gonna process T, right? Or maybe actually maybe I want to say like T dot value, right? And then I want to recurse on T dot left, and then recurse on T dot right. Right? This is pre-order because the parent comes before the two children, right? And so you can think of like, or if I think of this recursively, I start at A, so I process A dot value, and then I look at A dot left. So now I'm processing this subtree, right? And so now I've got B dot value, and then I process its subtree, which is D. So I process D dot value. It doesn't have any children, so these recursive calls don't do anything, and then I return up the call stack, and I get back to B. And so now I'm looking at B dot right, so I process E dot value, and then return up the call stack all the way to A, and then I process C, right? That's pre-order. Post order is, of course, the same thing, except now I um, I put my recursive calls first, right? So I'm going to do t.left. And I'm going to do t.right. And then I'm going to process t.value, right? So here I'm looking at this entire tree. Wait, oh yeah. I start by looking at this entire tree. I recurse on the left subtree. I recurse on the left subtree again, right? So I've recursed all the way down. I recurse on the left subtree, which is null, the right subtree, which is null, and now I process D. So I processed D, right? And then I pop up the call stack. So I finished the left call. So now I make the right call. And so I'm looking at this tree. The left and the right are both null. Now I look at E. And so I get E. And then I pop up the call stack again, and then I look at B, right? And now I finished this tree. So that's the left. So now I can move on to the right. So I get this. Of course, its children are null. So I process C. And then I've looked at the left and the right. So now I can process A. Right? That's a post order. Of course, if that's pre-order and post order, then in order is just I do left, I process t dot value, and then I do in order t dot right. Oh no, something wrong with the cursor. Is the cursor moving slower than it means to? Oh gosh, I don't know. Is that just you? Is that happening for anyone else? Is my writing messed up? Okay. All right. Um, yeah, sorry. I don't have a good answer for that. But yeah, okay. So right, all we've really done between pre-order, post-order, and in-order is switch around at what point in the process we actually process t dot value, right? So if I'm doing an in-order traversal, um, I start by recursing on the left, right? I recurse on the left. I recurse on the left. There's nothing here. So I process D. I recurse on the right. There's nothing there. So I pop up the call stack. I've done the left side of B. So now I can do B. And then I recurse on the right. So I get E. I've done the left. I pop up the call stack. So I've done the left side of A. So now I can do A. And then I can do the right side of A, which is C, right? So I get this order. The nice thing about depth first searches is right, they're very easy to write recursively, right? And in particular, we can think of these as manipulating a stack, right? So another right, we've talked about how to like turn recursive algorithms into iterative algorithms by making the call stack explicit. We can do that here by, I'm going to redraw this tree down here so I don't have to keep like trying to scroll. Okay, so A, B, C, D, E. Okay. So if I want to write like an iterative, let's do maybe like an iterative pre-order or something, right? So I start by pushing A, right? And then while the stack is not empty, I'm going to say, I'm going to pop a node off the stack. I'm going to process it. And then I'm going to push n dot left. And then I'm going to push n dot right. right? So if we think about making the stack explicit here, um, I start with a stack that just contains a. I start with a stack that just contains A because I pushed A, right? Then I pop A off the stack and I process it. I'm going to write A out here, and then I push B and C onto the stack, right? So I push. Uh, wait, let's just erase and then go back. So I push B and C onto the stack, and now I look at B. I process B and pop it off the stack, and then I push its children, which is D and E, onto the stack. Oh wait, sorry, I did this backwards, didn't I? It's a stack, not a queue. So I start by popping C off the stack, right? So maybe I want to say right and then left. Right. So now I can correctly do this, where I push C onto the stack, then I push B onto the stack, then I pop B off the stack, I process B, and then I push E and D onto the stack, right? Now I pop D off the stack, process D, and then D doesn't have any children, so I don't push anything. Now I pop E, process E, and then E doesn't have any children, so I don't push anything. And then I pop C, process C, and C doesn't have any children, so I don't push anything, right? And so this gives us ABDEC, which is our pre-order traversal. To do a post order or an in order, you just kind of mess with the way the call stack looks, right? But the idea is a depth first search kind of gives you like you can think of a depth first search as somehow using a stack to keep track of your traversal. This turns out to be a helpful way to think about breadth first searches, because a breadth first search is what happens if we replace our stack with a queue, right? So instead of this, I can say maybe like and queue, right? And then while queue is not empty, I can dequeue it, and then I can enqueue the right and the left. Only this time, I think I probably want to say left and then right because queues work backwards. Right, so if we think about this in terms of a queue, I start by enqueuing A, and so I process A, or I dequeue A and I process it, so I get A, and then I enqueue B and then C, right? And I processed A. Now I look at B, I process B, and then I enqueue D and E, and I've dequeued B. Now I look at C, I dequeue it and I process it. It doesn't have any children, so I don't enqueue anything. Now I dequeue D. It doesn't have any, I process it and then don't enqueue anything, and then same thing for E, right? So this gives us our breadth first search, right? So maybe the moral of the story is DFS is a stack, DFS is a queue, right? Okay. Different places where you might see these traversals come up. Oh, actually, I think before that, I want to talk about constructing a binary tree out of a traversal. So let's suppose we're given a what is it, like a post order traversal, right? So, okay. If I'm given some sequence of nodes that I visited, right? Maybe A, B, C, D, E. And I know that this is a post-order traversal of a particular binary tree. I can reconstruct the binary tree by every time I can iterate through my traversal, right? And just run this thing backwards. So every time I get something, every time I see a node, I push it onto the stack. If I see a node and there's two things on the stack, I pop them off the stack, make them children, and then push the new tree onto the stack, right? So I've got A on the stack, then I've got B on the stack. Now I see C, but I've already got A and B. So I'm going to pop A and B. I'm going to create something like this, and I'm going to push this onto the stack. Then I see D, so I'm going to push D onto the stack. Then I see E, but I've already got two things on the stack, so I can create E with C, A, B, and D, right? And then I push that onto the stack. And then by the end of my traversal, I should have one tree. Uh, yeah. So this is sort of how you can reconstruct a binary tree out of a post-order traversal. You can think of this as like I don't know if you've seen like reverse Polish notation calculators, right? So you do like 3, 5 plus 6 times or something like this, right? And the way you think about this is like pushing a 3 onto the stack, pushing a 5 onto the stack, then you add them to push an 8. And then you push a 6 and then you multiply them to push a 48, right? So this like evaluates to 48, right? Um, and so you're sort of doing the same thing here, where you push the 3, you push the 5, you see the plus, so you pop two things and you push an 8, and then you push a 6, you see the multiply, so you pop two things and you push a 48, right? It's the same thing, except now every time you've got things available, you pop them, and instead of like the operation you're doing is building up a tree. Um, in particular, you can think of a post-order traversal. Like you can think of this as a post-order traversal of the expression tree, right? So we can like write our tree like this, right? Um, so this tells me that I've got 3 and 5. I'm adding them at this node. I've got 6, and I'm multiplying them at this node, right? So this is sort of an expression tree. If I do a post-order traversal, it gives me the reverse Polish notation. If I do an in-order traversal, it gives me sort of what I would like how I would write this normally, right? If I correctly parenthesize it, right? So I could do an in-order traversal, and this would give me like 3 plus 5 times 6, right? Of course, it wouldn't give me the parentheses here, but it would give me like a way of writing this out appropriately. An attendance poll for today is why is it true that so obviously right given a post order traversal we can reconstruct a tree using this algorithm. I encourage you, I know I kind of sped through this, but I encourage you to think about this a little bit more, and maybe the attendance poll will help with that. Why is it true that you can't do that with an in order traversal? Like if I give you an in order traversal of a tree, um, why, or I guess maybe I shouldn't uh give that part away, but like can you given an in order traversal, can you reconstruct the tree that it came from? If so, how? And if not, why not? Right? So I'll just say that attendance poll. Can you go in order the tree? Why or why not? Okay. Maybe I'll give a minute for people to think about this and maybe shout out answers if they have them. Any thoughts? Say the question again. Yeah. So I kind of went over an algorithm for taking a post-order traversal of a tree and reconstructing the tree that it came from. Um, can you do this? The question is, can you do this with an in-order traversal, right? So if I gave you this in-order traversal, right? 3 plus 5 times 6 of this exact tree. Is there an algorithm that would let you reconstruct this tree? If so, what does that algorithm look like? And if not, how do you know that there isn't an algorithm that does that? In 264, wasn't it said that one any traversal was insufficient to uniquely reconstruct a tree? Yeah, I guess you do make some assumption on the you assume, I think you have to assume that it's perfect, right? Because for this algorithm, you only pop something, you only pop two things off the stack when you've got two things, right? Um, so you assume that it's a perfect binary tree. That is a good point. I'll say perfect. Okay. But the uniqueness thing is sort of the issue here, right? Like even if I know that this is perfect, the point is I could parenthesize it like this, or I could parenthesize it like this, right? It depends on how I want to associate things. And so with the in-order traversal, this tree and um, this tree, these two trees are non-isomorphic, but they have the same in-order traversals, right? And they're both perfect. Okay. Maybe the next thing to say is a good segue into binary search trees. So again, if you remember from, well, actually, I guess maybe I should pause to see if there's questions. All right, if there's no questions, um, if you all remember the definition of a binary search tree, right? Uh, the left child is less than or equal to the parent, which is less than or equal to the right child, right? So for example, an example of a binary search tree is I could have 5 here, I could have 3 here, I could have 1 and uh, 4 here. Sorry, I couldn't think for a minute. And then I could have like 8 here. right? Um, or like everything on the left is less than or equal to the parent, and everything on the right is greater than or equal to the parent, right? This is a binary search tree. If I had a 6 here, this would not be because the 6 is greater than the 5, right? Um, and to kind of give something away here, the reason we care about this is because if you have a particular value, I know which subtree it's going to live in, right? If I want to look for a 4, then I know I don't have to look at the right side because it's gonna necessarily be on the left side. Um, in particular, if you have a binary search tree and you do an in-order traversal on a binary search tree, you get something that's sorted, right? So a particular way of sorting things is to take everything that you have, insert it into a binary search tree, and then read off the in-order traversal, right? So this is like 1, 3, 4, 5, 8, right? I look at 1, 3, 4, and I go up to 5, and I look at 8. Um, yes, okay, great. I guess it's almost 9:40. So maybe I'll call it here, and then we'll pick up tomorrow with BSTs. Any other questions before class is over? I'm also just going to stick around for a couple of hours because I have office hours. Yummer, is Yummers a comment on BSTs? No. Okay. All right. Well, I'm going to close the whiteboard. Regarding the yes, okay. So we're working on finalizing the autograder for that. Once that is finalized, we will release some of the small and some of the large test cases. And in terms of the runtime being graded, most likely there's going to be a time limit. Um, and so you get points for all the test cases that pass within that time limit. Um, so in particular for the smaller ones, that's not going to matter because it's going to be like more than enough. But for as they get larger and larger, your program is going to have to be more and more efficient to complete the test case within that time limit. Um, like I said, we're still figuring out exactly what those test cases need to look like and whether or not the autograder can handle them. So once all of that has been finalized, I will make a post on Piazza, releasing like specific cutoff times and test cases and stuff like that. Good question. Okay, I'm gonna go ahead and stop the recording now.